Okay, last time we finished chapter 17, electrochemistry. So we're off to nuclear chemistry now to see what glows in the dark, I suppose. So we're talking about nuclear chemistry in this chapter. So that obviously involves radioactivity. So let's talk a little bit about radioactivity. Radioactive nuclei will spontaneously decompose into smaller nuclei, and that's what's really known as radioactive decay. And we say that something is sort of radioactive if it is unstable. The decomposing does involve the nuclide emitting particles and also some type of energy associated with it. Now, nuclear sort of processes are different, as we'll talk about, than sort of chemical processes. We do sort of make new things as a result of things basically going through radioactive decay. Sometimes referred to as a nuclei is what basically our radioactive guy and our particles that are in our nucleus. Our parent nuclei is the nucleus that's undergoing the radioactive decay, and the one that's sort of produced as a result of that is sometimes referred to as the daughter. Usually, all nuclei with 84 or more protons on the periodic table there is usually radioactive. That usually brings you to kind of like the bottom row there on the periodic table, where you don't do too much with. But that is where we see a lot of those things like uranium, a lot of those sort of man-made elements as well. Like Einsteinium, Nobelium, all those kind of guys, are found in that sort of area. Now, there's different types of radioactive decay, and we remember our friend Rutherford. Rutherford did what? He did that experiment with gold foil, right? And he shot alpha particles at it. He discovered three types of sort of radioactive particles or rays that we come across. And the first one is actually an alpha particle. Alpha particle is abbreviated with the alpha symbol. It is also sometimes abbreviated with the helium symbol as well, because frankly, it is kind of like helium pretty much. So a lot of times they'll be used sort of interchangeable in sort of nuclear chemistry. Alpha particles are helium. It has a +2 sort of charge unit and a mass of 4 AMU. And it basically is like a helium. It's sort of like your positively charged radioactive particle. Now, your beta particles or beta rays, they have a charge of -1. They're pretty much electron-like. They also will use the beta symbol, um, or they will also use the electron symbol there because it is a -1 sort of situation that's occurring. Now, they're basically like electrons, so they're sort of our negatively charged particles. Gamma rays are pretty much pure energy. They usually will use the gamma symbol there. And if you remember sort of the electromagnetic spectrum, you typically will find gamma rays at one end, and that is usually the short wavelength end, past X-rays and things of that nature. And if you remember, wavelength is proportional to or related to the amount of energy. Shorter the wavelength, higher the frequency and higher energy. And it's kind of the farthest as you could go there past X-rays. In addition, we'll talk about some other sort of very common radioactive particles and situations that we come across. We have sometimes they will emit what is referred to as a positron. It's like an electron with a better attitude. It is positively charged pretty much, and it does use the same symbols as a beta particle, but except it's +1s instead of -1s in there. Also, occasionally, a type of sort of nuclear reaction that can occur is what's sometimes referred to as an electron capture, and it is pretty much what the name sounds like. You basically shoot an electron and it captures it, and that obviously can cause a reaction to occur. So when we look at our numbers here, right, up on top and on the bottom, right, when we look at something like this, right, our top number is the atomic number, right? No, it's not. Our top number is the mass number. That sounds better. And our bottom number there is the atomic number. When we do write isotopes like this, sometimes isotopes, which a lot of times there are different radioactive isotopes. Isotopes, as you may remember, are basically the same element, but they have different masses because they have different numbers of neutrons. Sometimes we do write isotopes like this, where this number here would be the mass number, right? So we do remember, hopefully, our definitions here. Our atomic number is the number of protons that there are in a nucleus of an atom. We can find the atomic number there on the periodic table. That is the number above the symbol, and that is your atomic number. Remember that the definition of atomic number is actually just the number of protons. It will also tell you the number of electrons if the guy is neutral, but the real definition is just the number of protons. The mass number, which is abbreviated A, and that's usually bottom left, the top right. I can't get that right here. It's a long week here. It's not there. Yeah. This number up there, top left, I think they call that, is the number of protons plus the number of neutrons. And the importance of sort of the mass number and the atomic number is, again, if you take your mass number minus your atomic number. Mass number is protons and neutrons. Atomic number is protons. So if you subtract those two, gives you basically the number of neutrons. So if you take the mass number minus the atomic number, you get the number of neutrons. Is the mass number on the periodic table? The answer is no. That number on the bottom is not the mass number. That is the atomic mass. And when you calculate something like mass number, atomic number, protons, electrons, and neutrons, they all should be positive whole numbers. And again, if you look on the periodic table, pretty much none of those numbers on the bottom are whole numbers. They're all decimals and stuff like that. So only the atomic number is found on the periodic table. Also really important in terms of atomic number and the number of protons. It is the number of protons that tells you what element you're dealing with. As you look on the periodic table, there is no element that has the same atomic number. So if you know the atomic number or the number of protons, which again is pretty much the same thing, you will know exactly what element you're dealing with. And again, there's our mass number and our atomic number. Here are some of those symbols that's very commonly seen when we go through sort of radioactivity and nuclear chemistry. A proton is something that's given off sometimes or involved, and a proton can be sort of symbolized by two ways, with a P and a 1 on top and a 1 on the bottom. And that's because we take the 1 minus 1 is 0, and hydrogen is the only element that does not have a neutron, right? Hydrogen has a proton, and an electron does not have a neutron. Everybody else has it. Hydrogen also can be used, the H symbol there. A neutron, very popular here in nuclear chemistry. It's abbreviated there with an N, a 1 on top for the mass number, 0 on the bottom. There's our electron, which is oftentimes called our beta particle. And again, our electron symbol, or our beta symbol is sometimes used. There's our positron. And again, it's pretty much the identical symbols to your beta particle, except that it is +1. And our alpha particle here, again, very common. Both of these sort of symbols are used to do so. So how do you know if you're given something that just says beta, the symbol for that, if it's the beta particle or the positron? It's probably pretty safe 99 times out of 100 there to assume that's going to be the beta particle. If it is the positron, they usually will put some type of indication, maybe like a little plus symbol there or something like that, or actually include the +1 over here. So usually if it's meant to be sort of the positron, they definitely will sort of point that out somewhere with a plus sort of symbol. If you don't see any of that and you just see sort of the beta particle, it's probably, again, safe to assume that it's actually a beta particle in the negative version of it, since they do sort of use really the same symbols for the most part. Now, when we talk about radioactivity, different types of rays can penetrate things like your skin and your body and lead, different amounts. Alpha particles there only penetrate about 0.01 millimeters of lead. Beta particles go a lot further, so you need a little bit more protection. And as you can see there, gamma rays just keep on going. So if you ever find yourself working with radioactivity, it's really important to know what type of emitter it is. And when we talk about things emitting, that means that usually something is being given off, some type of particles being given off. Uh, So, if you're dealing with something that's an alpha emitter, you might not need as much, say, protection as you're dealing with something that's a gamma emitter where you might need a lot of lead, some distance and stuff like that. So it's really important if you ever find yourself, like I said, sort of working with radioactivity, that you understand really what type of emitter it is so that you sort of have the proper sort of protective equipment to do it. But in terms of lingo, in terms of language here, as you sort of mentioned here, emitting usually means something's given off. So usually what that means is that guy will end up on the product side of the reaction. When we talk about something being bombarded, or like an electron capture, so if we like bombard something, or like an electron capture, that implies that that sort of guy is going to find itself on the reactant site, like it's being added. So these are very common sort of names that are sort of seen. Here again are our symbols, and like I mentioned before, as you can see here, they oftentimes will sort of indicate it is either the beta particle or the positron. So let's talk about balancing nuclear equations, which is super difficult. Not really. You just need to know how to add, I suppose. That's all you really need to know. So one of the major differences between a nuclear reaction and nuclear equation and just a basic chemical equation is really what is happening. As you may know, in a regular run-of-the-mill chemical reaction, it's all about we're going to break bonds and we're going to make bonds. And that involves obviously bonds, electrons. So basically, the only thing that's involved is electrons. And that is why when we balance equations in a chemical equation and a chemical reaction, we should have the same elements on both sides, right? Because we're not touching anything in the nucleus. We're just touching electrons, basically. So however many protons we start with carbon, he'll keep his protons, and he'll still be carbon on the other side, maybe attached to some other things along the way. And that is completely different than what happens in a nuclear reaction. In a nuclear reaction, pretty much all we do is play with what's inside the nucleus. So we play with protons, neutrons, and those dyes actually change. We sometimes maybe change some protons into neutrons, some neutrons into protons. And because of that, we do not get conservation of the elements like we get in a chemical reaction. So if we started with carbon, we may not end with carbon in a nuclear reaction because it will actually change elements. So because of that, the way that we go about balancing a nuclear equation is we want to make sure when we look on the left-hand side of the equation and the right-hand side of the equation, that all of the mass numbers basically add up to the same number. So if we take an accounting here, that's a 235 plus 1 is a 236. Over here we have 138, I think 96, and a 2 as we would multiply it there, which would also give us 236 on the right. So that is balanced in terms of our mass numbers. The other way that we want to make sure our equation is balanced is through atomic number. And we would do basically the exact same thing here. We would add up the bottom numbers, which is 92 on the left. We got a 55 and a 37 and a 0. And that's going to be 92 on the right. So this would be considered a balanced nuclear equation because all the mass numbers on the left add up to all the mass numbers on the right, and all of the atomic numbers on the left add up to all the atomic numbers on the right. So how would these be sort of given to you? A couple of different ways. Perhaps you had something missing, like 23592 uranium plus a neutron goes to 138. 55 cesium plus who knows, and a couple of neutrons, right? So if you have this situation where maybe you're trying to find what is missing in this case, the most important number to figure out first would be the atomic number, right? Because if I know the missing atomic number, I could go to my periodic table, which is your friend when you're doing these type of things, and then you could figure out, what element's missing. So if we did that again, we would have 92 here on the left. On our right, we basically would have just 55. So frankly, if we just take 92 minus 55, that's going to give us our 37, which is sort of our missing element. We then could just pick up our periodic table and find number 37, like it shows there, and that's our friend RB. We then could do really the same thing for the mass number. On the left-hand side there, we have 236. On the right-hand side, we have 138 and 2, which is 140. So we basically can say 236 minus 140, and that will give us our missing mass number, which looks like 96 in this particular case. So I would say having a periodic table, and if something's missing, I would approach the atomic number first and then get to your mass number. Now, remember that in this type of reaction, something that's missing could also be a particle. So if you look at it, it doesn't seem like maybe it's an element, but it's kind of like a weird negative type number. Maybe it's like a beta particle, right, that you're missing or something like that. So I would say most of the time it's probably going to be an element from the periodic table, but it definitely could be some type of particle that's missing. In addition, a lot of times in these type of problems, they'll just tell you, hey, this nuclei went through alpha decay. And when it says something like this guy went through alpha decay, what that means it's going to emit an alpha particle. The alpha particle will be on the right-hand side, and then you can kind of figure out what it will become in that case. Any questions on that there? All right. All right, so let's take a look at one here. We have PO212 decays by alpha emission. We want to write the balanced nuclear equation for this. So when we look at this, here's what we want to look at. We got PO and 212. That is our mass number, which is on top. We would go to the periodic table and find our PO, and our PO looks like an 84, if I'm not mistaken. It's going to decay by alpha emission. Again, alpha emission means the alpha particle is going to be on the product side, which you could use the alpha symbol. Or if you wanted to, you could also use the helium symbol for the alpha particle, whichever one you want to do. Now we pretty much got us set up to figure out what's going on here. We have a 2 on the right and an 84 there for our atomic number on the bottom. So if we subtract those two, that is a missing atomic number of 82, which if we go to the periodic table, we will see lead there is number 82. When we come to our mass number, we got a 212 and a 4, and that's going to give us a 208 as our missing mass number. So again here, we can find our atomic number, get our symbol, and figure out our mass number. We are balanced on the left there is 212 in terms of the mass number. We're balanced on the right there, 208 and 4 is 212, and 84 on the left, and 82 and 2 is 84 on the right on the bottom there. Any questions on that one there? So as we talked about a second ago, there is again a major difference between chemical processes and nuclear processes. As I mentioned before, our chemical reactions are pretty much all about electrons, breaking bonds, making bonds. Nuclear reactions involve a lot of replacing or changing things in the nucleus. There's also, as we'll talk about, a pretty big energy difference because of that. There's a lot more energy sort of in play as you try to go into the nucleus and sort of convert things that are inside the nucleus versus just breaking some bonds on the outside and making some bonds on the outside. So that's why in a lot of cases, nuclear processes will release a lot more energy than even your kind of most exothermic type of chemical reaction. So it definitely, because of your kind of playing with the nucleus, will give off a lot more energy. We'll talk a little bit about each of these, sort of what is going on in each of these cases, and talk about sort of what's sort of really happening here with the change. We're not going to worry about the neutrino here, so we could just we could ignore it for our purposes here. So if we look at a beta decay, we decrease the neutrons by 1 and increase the protons by 1. We are essentially taking a neutron and we're converting it into a proton, and sort of the byproduct of that conversion is we're going to release a beta particle as a result of that. Now, ultimately, what happens here is the change is 0 minus 1, which means we actually need to go up in atomic number to account for the minus, and the mass number overall really doesn't change. So we see that here, 6 on the bottom, 7, and minus 1 gives us 6, 14 on top, and 14 and 0. So you might be wondering, we are changing a neutron into a proton, so there is some change actually happening. So if we think about sort of what's happening here, we take our sort of carbon here in a play-by-play situation, which is not exactly how it perhaps happens. We are going to remove a neutron. So we're going to minus a neutron, which is out here. And that would take us then to 13, right? And we're going to add a proton as a result of that, which takes us from 13 for our mass number back to 14 for our mass number, because we basically swapped out the neutron back to the proton. But what really happens, though, is because we're now adding a proton, we go from a atomic number of 6 now to an atomic number of 7, and now we become our nitrogen in this case. So there is really a change that's happening in the mass number. We're actually lowering the neutrons by 1, and then we're replacing that neutron with a proton. The reason, again, the mass number doesn't change because it's the number of protons and neutrons, so you basically just swap places there and you will stay the same. But we are really swapping the numbers of protons and neutrons in this particular case. Positron, here's our positron, which again looks very similar to our beta particle. In this case, it's sort of the opposite. We're taking a proton and we're going to actually make a neutron in this case. The result of that is our positron particle will be released. Overall, the change is going to be nothing happening in our mass number. So again, if we kind of do step by step here, we're going to take a proton out, which means my mass number is going to go down by 1, and my atomic number will go down by 1, which takes me 10 to 5. But then we just made a neutron, which means I need to add 1 back to that guy, which is going to take me to 11 and 5, and that's going to take me to boron at the end. Again, overall, the mass number stays at 11 in this case, but we're swapping basically a neutron for a proton in this particular example. In this case, we actually decrease the atomic number by 1 because we are converting that proton into that neutron. Any questions on that there? Super zoom just in case. All right. Electron capture, as I mentioned before, shows the electron on the reactant side, like it is being captured. And in this case, what's happening is we're actually combining an electron and a proton, and that will make our friend the neutron. So we're basically combining an electron and a proton to make a neutron. And basically, in this case, we do end up with no change there in the mass number. Kind of the same process is going to happen if we take our 3718. We're going to get rid of a proton, which means we're going to get rid of a number on top and bottom. We're then going to replace it with a neutron. So we're going to go back. That's a net of no change there up on top. Bottom guy changes there. And that is how we get to our new guy in this particular case. So again, even though overall it looks like maybe nothing has changed in terms of the mass number, we are converting some of these particles into other particles, and we do have that sort of change happening. Probably the biggest change you'll have is when we have an alpha decay. the mass number will overall change by 4, and the atomic number will change by 2. Now, radioactive decay or fission, which is the process where we take something and it will continue to go through a decay process until it pretty much kind of reaches a neutral, not neutral, but a more stable sort of situation. And that could be spontaneous. So spontaneously, there are certain elements that will just start decaying away and will continue on. And typically in a fission reaction, you usually will get a couple of new nuclides, and you also will generate some neutrons coming out. In addition, there's usually a pretty good amount of energy being released in this case. That is why they use like nuclear fission reactions for things like nuclear power plants. It gives off a lot of energy, as we'll talk about a little bit later on. Now, as we will also see, there is not necessarily a guarantee every time something goes through, say, a fission reaction where it breaks apart into a couple of new nucleuses and gives off some energy, that you always get the same thing. So you don't always necessarily get the same products when these things kind of go through these sort of fission reactions. There's a lot of times you get a good combination of things that come up a lot, but you can get different things that are going to be produced on the product side. But typically always produced is some neutrons and also some energy and a couple of new elements. We will also talk about a little bit later on that you could also sort of help that process along, or sort of initiate that process of fission by frankly shooting a particle at something that's stable. And when you shoot a particle at something that's stable, it becomes quite unstable at that point, and it will sort of kick off that sort of fission reaction. Here's a table similar to one you have in your book of basically all the things that we just talked about there. All right, so why don't you do this one here? Write the balanced equation for the positron emission of potassium 40. If you have a periodic table, that would be helpful. Don't have a periodic table. Okay, so let's take a look at this one. Potassium 40, once again, written this way, that is our mass number. So that's what we're going to start with. We could obviously use our periodic table there to get our atomic number, which is number 19. It is going to go through positron emission. So emission means our positron particle. It's going to be over here on our product side, which you can use the beta particle, or you can use the E for it as well. So now we want to look for our missing sort of mass atomic number. I got 19 and 1 on the other side. That means that's an 18 that's missing, and that is our friend argon. Up on top, I got 40 on the left, 0 on the right, and that's going to be a 40 right there. And there it is. Yeah. Questions on that one? Once again, in place of this, you could do the E instead of the beta particle if you wanted to. Any questions on that one? All right, a few more here just to make sure. You're gonna say agree with me. There it is. All right. All right, write some balance equations for each of these here. See what you come up with. Okay, so let's take a look and see. So we'll start in each of these cases, we have the mass number given to us. So we're going to start with our uranium. It's got a mass number 238. Once again, we could go to the periodic table there and find the atomic number of 92. Once again, emission means the particle will be on the product side. And again, you can use whichever sort of alpha symbol you like, the helium or the alpha symbol. Is a 4 and 2 situation. That's going to allow us to find our missing atomic number. And that's basically going to be 92 minus 2, which will give us 90. And we go to periodic table for number 90 there. That's a TH, it looks like. For our mass number, we're going to do the same thing. We got 238 on the left, 4 on the right. It's going to give us a 234. Any questions on that one there? Next is neon with say 24 and an E. There we go. That's going to be a atomic number of 10. Once again, an emission means we are going to have the particle on the product side. beta is the -1 version there. Again, you can use the beta symbol, R the E. Remember, because this is actually -1 there, we got to go 1 up, which takes us to 11 for our missing atomic number, as 11 and -1 is 10. That's going to be sodium. Going to our top there, 24 on the left, 0 on the right, leaves us a 24 there on the right-hand side. Here we got nitrogen with a 13, atomic number going to be 7. Positron emission in this case looks just like the beta, but a positive number. Because that is a positive number, we're actually going to subtract that. That's going to be 7 minus 1, which give us 6. Going to periodic table there, number 6 is carbon. And 13 up on top. Any question on those two there? Lastly, we got a little beryllium action. Feel like that's 4. This is actually an electron capture. So again, the wording sometimes you'll hear is electron capture, means that is reactant side. Bombardment means also reactant side. So here we're going to add an electron. We're just going to simply add what we got going on the left here. So that's 4 and -1, which is 3. And that's 7 up on top. And 3 is our friend lithium from the periodic table. Any questions on balancing nuclear equations? We should just have a whole test of that. It'd be pretty good. It's like add, I suppose. Any questions on how to do that there? Huh? So again, obviously periodic table your friend, atomic number your friend, calculator your friend, just in case. All right, then let us continue on and talk about some other things, including the classic favorites, the N to Z ratio. That is, N to Z is neutrons to protons, basically, as Z is the atomic number. That's our kind of neutron to proton ratio. And it is a measure of stability. So we can look at the ratio of neutrons to protons and use that to help us understand whether or not maybe something's going to be stable or unstable. Now, if we determine, for example, that the neutron to proton ratio is too high, then what happens is we actually will want to convert some neutrons into protons through a beta decay process. So what that means is, we'll see it in just a second, but it is as simple as your ratio is too high from the stable line, if you will. So we're going to try to bring it back down, and the way it's going to do that is a beta decay. So you could write the reaction for what's going to happen if you do have a too high ratio by taking whatever you're starting with and taking it through a beta decay reaction. That should give you a new sort of element or nuclide that is more stable. Will it mean that it will be perfectly stable at that point, just going through one beta decay? You might get lucky, but you might not get a perfect sort of ratio that you're looking for. But it should definitely move you closer to that kind of nice, perfect ratio. It shouldn't move you away from it. Now, the opposite is true. You could have a ratio that's frankly too low in terms of what's going on. And in that case, we're going to do kind of the opposite. We're going to actually convert our protons to neutrons. And you have basically 2 options to do this. It could either be a positron emission or an electron capture. So the thing could go through either a positron emission or an electron capture to try to be a better ratio. It can also do an alpha decay, but it's not as efficient. So for us in here, although it can technically do an alpha decay, if you find the ratio is too low, you should do one of these 2 processes here. And we'll leave the alpha decay off of it, and we'll just go with those 2. Now, you might be asking, if I'm doing 2 different sort of things, perhaps a positron emission and an electron capture, will I get the same thing? And the answer is actually, yeah, you will get the same thing. And if we look at our guy that we just did here, which was an electron capture, if we did the same guy, but instead of an electron capture, did a positron emission, we would end up with pretty much the exact same guy as our product. So both of those guys will give you the exact same product. if you do an electron capture or a positron emission. So you do have an option on that case as to which one you want to do. In this case, what we're going to do is convert some of those guys, and we're going to bring the ratio up closer to that more stable arrangement that we're looking for. Now, how do we know if if it is stable, or what is a stable sort of deal? And the answer is there is the valley of stability, or in some books they call it the belt of stability, whichever one you like. And this is essentially this sort of smear here. And that is going to give us really our sort of acceptable, stable ratios. Now, if you are somebody that is between 1 and 20 in terms of its atomic number, then the acceptable neutron to proton ratio is 1, and that would be considered stable. And again, it's in this situation, it's either you're higher or lower than 1, and as to which way you're going to go. If you're somewhere between 20 to 40, you now move to like a 1.25 is an acceptable ratio. 40 to 80, 1.5 is the acceptable ratio. Anything above pretty much 84 is going to be radioactive and not going to be stable. So as you can see, there is sort of, to be truthfully honest with you, a gray area, if you will. As you can see, the first one goes 1 to 20, the next one starts at 20 and goes up, and it goes to 40, while the next one starts at 40 and goes up. So there is sort of a grayish area where sometimes they'll go like, it's kind of in that area, still okay, because it is that gray area. So just for the purpose of this class, so there is no gray areas. We're just going to roll with either it is that number, and if it's not, it's too high or too low, and you can just do it. And we'll kind of use them as sort of absolutes. But in reality, obviously, there is some grayish area as you bleed over kind of between your transitions of like 20-ish and 40-ish in terms of that. I will try not to give you a 20 or a 40, and we'll just kind of bleed over and go absolutely sort of positively there. And then what we're talking about here again is if we're too low, we're going to try to bring us up closer to that valley of stability. And if we're too high, we're going to try to bring it back down by doing those conversions. Again, if it is too high, we're going to do our conversion, beta conversion there, and not, we're going to do a positron emission or an electron capture to bring it back up. All right, so why don't you try that here? Predict what kind of radioactive decay magnesium-22 will undergo, and also write the reaction that will happen in that case. So take a moment there and see what you come up with. So let's take a look. So first off, we're looking for our neutron to proton ratio here. So we need to figure that out, I guess. So we have magnesium-22, which is our mass number. We could go to the periodic table there and find that our atomic number there is 12. That means that our number of protons here is 12, or our atomic number. And if we take our 22 minus 12, that will give us our number of neutrons, which in this case looks like 10. So if we take our neutrons divided by our protons here, we will get a ratio of 0.833. Remember that this is a guy between 1 through 20 in terms of its atomic number, and that means that the acceptable ratio is 1 in this case. That means that this is actually too low. So we do need to bring it up. So we're like down here, we got to kind of bring it back up. Now, to do that, we do have the option here when we're too low to do one of two things, either an electron capture or that positron emission, as we talked about, right? So if we did our 2212 magnesium, did a little electron capture action, that's going to give us an 1122 sodium. Again, you could also have done the positron emission, 2212 magnesium, 0 plus 1, and then that will get you 2211 sodium in this case. So this is what should happen to go through this decay process. We should produce sodium in this case. And if we actually look at sodium's ratio in this case of what we just produced, for sodium here, we have in terms of protons 11. Neutrons would be 22 minus 11, which would be 11. That gives us an N to Z ratio of 11 divided by 11, which is 1. In this case, it actually got us to that perfect ratio. It definitely brought us up towards it. This is, again, not always the case that you will hit the perfect ratio after you do the decay process. But once again, it should move you closer. And if you had a question like this, that would be all you would need to do is the sort of first process here of the decay process. You wouldn't have to keep going until you get the right ratio or anything like that. So you just have to kind of do the first step there. Any questions on that one there? All right, let's try another one here. Our friend Krypton 85 is stable or radioactive. If it's radioactive, what's going to happen with it? So let's take a look at this one. Once again, we're given the mass number. Going to periodic table there, Krypton is like a 36, I think. Seems like a good number. There we go. All right, so we're looking for our N to Z ratio here. So obviously our Z is going to be 36, or protons, and our neutrons will be 85 minus 36 will equal our neutrons, and that's going to get us there. It's like a 49. We'll divide our neutrons by our protons, and we will end up with a ratio of 1.36, I believe. Now, this guy is in that 20 to 40 sort of numbering. So remember, at 20 to 40, we're looking for an N to Z ratio of 1.25. So that means we are too high in this case, right? So we do want to kind of bring it down by doing those conversions. And in this case, that's going to be our beta decay. It's going to do that. So we would take our 8536. We would do our beta decay. That means we're going to go to 37 and 85. 37 being, that's RB there, right? I believe. RB in this case. Once again here, obviously, the first answer to the question is it is not stable, right? Because it is too high, the ratio. It is radioactive. It will go through this process to try to make itself better. And if we look now at what we just produced, we have 37 for our protons, and 85 minus 37 is 48 for our neutrons. So we take our 48 divided by 37. We're going to get about 130. So we are dropping at least down closer to the acceptable sort of range. Again, we didn't hit perfect, which is very common. You won't necessarily hit a perfect sort of ratio, but you should definitely be moving in the right direction. Any questions on that there? Okay. So N to Z ratio is something that we can look at to help us decide stability and also figure out what type of decay it's going to go through if it is radioactive to move itself closer to being stable. There are some other sort of things that we look at in terms of stability, and a few of those other things that we look at involve magic. So besides the N to Z ratio, the actual number of protons and neutrons do affect the stability. If we look at this little table at the bottom, pretty much kind of the best situation for stability seems to be when you have even number of protons and even number there of neutrons. There's like 157 stable nuclei in that sort of arrangement. The next sort of best thing in terms of stability is if you still have even protons, odd neutrons. You got about 53 of them. Next best situation, odd protons, even neutrons. Worst situation in terms of stability, as you can see, is a double odd shot there. Odd protons and odd neutrons. There's only 5 sort of stable nuclei that have that sort of arrangement. So best situation, positive, positive. Worst situation, odd and odd. They say positive, positive, even, and odd there. In addition to that, most stable nuclei, as we see there, do have that even number of protons and neutrons. If the total number of nucleons, and this is a name that you sometimes hear a lot in nuclear chemistry, Nucleons is pretty much the stuff in the nucleus. So that's your protons and your neutrons. It's essentially your mass number. So that's like your protons and neutrons. It's basically everything in the nucleus is what a nucleon is. Now, if the total number of nucleons add up to a magic number, the nucleus is more stable. It's kind of like an electron configuration where everybody tries to hit noble gas configuration, and that's really a stable sort of configuration. Things are most stable when the neutrons or the protons are either 2, 8, 20, 28, 50, 82, and your mega number of 126. I'm going to play those a little later tonight to see how I do those numbers. So if you have sort of those arrangements, it's kind of more stable. And again, it's sort of like getting to like the noble gas configuration in terms of what's in the nucleus. So there's a few other things to look at. If you have the ability to do the N to Z ratio, that's a good thing to look at. Just kind of quickly looking at something and going, oh, we got even or odd, that's probably not going to be stable or going to be stable. That's a good way to kind of do it as well. Now, a decay series is a series of radioactive reactions that occur until basically the parent nuclei comes to the daughter nuclei, and it keeps kind of going through the decay process until kind of something stable gets hit at some point, and it sort of stops that process. So all radioactive nuclei are produced one right after the other, and this is what is called a decay series. Now, there's a couple of different ways that you can sort of do a decay series. The easy way is perhaps, I don't know if the easy way, but one way to do it is basically you just write nuclear equations. And the product of your first nuclear equation becomes the reactant of your next one. And then the product of your next one, reactant of the next one. You just kind of keep following through the decay process. Now, if you're interested maybe in just like, what do I get at the end of this process, at the very end, and you're dealing with alpha and beta decays in these series, you can basically subtract from the mass number 4 for every alpha decay. So you can take 4 for every alpha decay that you do. And from the atomic number, you can subtract 2 for every alpha decay from the atomic number and the mass number. And you could also add 1 for every beta decay that you do. So for example, let's just say that we had uranium. Oops, come here. Let's just say we had uranium 238. I squished it in there. And let's just say, obviously it's 92 we're starting with. Let's just say it went through, I don't know, we'll do the first little part of it maybe. Let me just see here. We'll do alpha, beta, alpha. Let's just say we did this little part of the decay series. So we have these decay processes happening back to back here. So what you could do is you really could just do equations if you like. And you can take your uranium 238 and your 92. And obviously the first thing that's going to happen is our alpha decay, which takes care of that guy. That would take us to 90 on the bottom, which would be TH. And up on top would be 238 minus 4, which would be 234. Then this guy that we just produced would now become our reactant, and it would go through a beta decay here, which is 0 minus 1. That would then produce a 91 234, and 91 is PA, it looks like. Then that guy that we just produced will go through another beta decay, which would then take us back to 92 and a 234, and that takes us back to uranium. And lastly here, our 234, 92 uranium will go through the last little guy here in our very short decay process. And have our alpha decay, which will take us to 90 to 30 in this case, which would again take us back to TH. So obviously, if it's a longer decay process, you can just keep doing that product to reactant, product to reactant. probably won't screw up too much. But if we just wanted to figure out, where we're going to end up, we know in this short little process here, we had 2 alpha particles, which means from our mass number and our atomic number, because of the 2 alpha particles, we need to subtract 4 twice, or 8. We also know that from our atomic number, we also need to subtract 2, as we're taking away that twice. Now we also have a couple of beta particles, which means from our atomic number, we need to actually add 1 back each time. So we started out here originally at 238 and 92. So 238 minus 4 is 234, minus 4 more is 230. 92 minus 2 is 90, minus 2 is 88, plus 2 is 90. And that is where we ended up, yeah, right there. So if you're just kind of interested in at the end and they're alpha, beta sort of guys, you could just kind of keep track, add them up, subtract it out. If you want to know what you get after each individual step, you obviously can do the equations. Again, whichever way you think is best for you, probably, to be truthfully honest, even though it's a little bit longer, probably safer to do the equations rather than adding things up and adding something along the way. They'll get you there. Now, this is obviously a process, as we'll see here, for something like uranium that actually splits off and has 2 different sort of pathways to do that. And we got up to like here, I think, or somewhere like that. But it will continue down until basically they both end up at the same spot, which is this sort of stable isotope there of lead. And it will continue this process. And again, very common sort of radioactive and nuclear sort of processes. There's always some type of diversion type of process that occurs. You don't necessarily always go the same pathway every time that these sort of reactions take place. Any questions on a decay series?